entropy change in the adiabatic reversible expansion of the ideal gas. Entropy change during adiabatic reversible expansion of ideal gas. Next, we know in the adiabatic reversible system, the heat exchanged with the surroundings is 0. dq is equal to 0. Therefore, if we calculate the entropy of the system, first let us calculate the entropy of the surroundings. See, the surroundings are neither absorbing the heat nor liberating the heat. Therefore, the del S of the surroundings is dq upon T. Here 0 upon T. That means 0. Del S of the surroundings is 0. Next, similarly, del S of the system, since when the surroundings neither lose nor gain the energy, system also neither lose the energy nor gain the energy. Hence, here the entropy of the system is dq upon T. Here dq is 0, therefore by T, that is equal to 0. That means during the adiabatic reversible expansion of the ideal gas, the entropy change of the surroundings is 0, entropy change of the system is 0, therefore del S total. Del S total means del S surroundings plus del S system. This is 0 and this is also 0. So, the net entropy change is 0. Therefore, not only here, wherever if you just see the word reversible, whether it is adiabatic or isothermal or any type of the process, if the just process is a reversible, then total entropy change is always 0. Next, the entropy change during the adiabatic irreversible expansion of the ideal gas. Entropy change during adiabatic irreversible expansion of ideal gas. Irreversible expansion of the ideal gas. Here in this irreversible process also, the surroundings are neither losing the heat nor gaining the heat. Therefore, del S of surroundings, del S of the surroundings is dq upon T. That means here again 0. Next, entropy change of the system. See, if we recollect the total entropy change of the ideal gases, so earlier we have derived one expression, that is NCV ln T2 by T1 plus NR ln V2 by V1. This is the total entropy change of any ideal gas which is participating in any type of the process. This is NCV ln T2 by T1 plus NR ln V2 by P1. Here, that means the gas is neither absorbing the heat nor liberating the heat. Therefore, this term is 0 here. Therefore, 0 is equal to NCV ln T2 by T1 plus NR ln V2 by V1. NR ln V2 by V1. Therefore, bring any term to this side. It becomes minus NCV ln T2 by T1 is equal to NR ln V2 by V1. Next, see now if we compare the magnitude of the left side term and magnitude of the right side term. Here in this case, it is a irreversible process. During any irreversible process, the heat that is being participating and the work done by the system will never coincide with each other. Usually in a irreversible process, the work done by the system is less and energy spent by the system is also less, but they do not coincide with each other. Now, if we compare the magnitude of the left side term and magnitude of the right side term, here the magnitude of this left side term is more and the magnitude of the right side term is less. Therefore, del S system finally it becomes negative. Here the logic behind becoming negative is, here during the adiabatic irreversible process, the gas is undergoing expansion by spending its own internal energy. When the internal energy is spent off, the net energy left with the gas molecules decreases, hence entropy becomes negative. Entropy becomes negative. Here see, entropy of the surroundings has already become 0. This is the entropy of the system. Therefore, total entropy change, del S total, is equal to del S system plus del S surroundings. Del S system is negative, this is surroundings is 0. The net entropy change is negative.